Greetings, this is Phi 21.170, and this is Mutation Explorer for Simple Graphs, a browser-based application that allows one to run the mutation game on predefined simple graph structures for a specified number of cycles or turns. A simple graph is defined as a set of vertices, as you can see in the definition panel here, and a set of edges. You can also think of them as nodes and links. A link is specified by two vertices or nodes and represents a bidirectional relationship between the two. So the mutation game starts by setting an initial value to each of the vertices of 0, except for the first, which we set to 1. To mutate a vertex, we simply negate its value and then add the sum of its neighbors to it. So, for instance, let's just imagine for demonstration purposes that we have a value of 1 in each of the nodes of our graph here. And we want to mutate node y. So we would take the value of y, which is 1, and negate it, turning it to -1, and then add 1 for each of the neighbors, which is 3. So -1 plus 3 equals 2. So this graph with a population with all of the elements being 1, if I mutate y will be mutated to 2. So the set of values at a point in time is called a population. Our starting population is called a singleton population. And each unique population derived from successive mutations of the graph, starting with the singleton population, is called a root population. So on each turn, Mutation Explorer selects a vertex, mutates it, and records a new population to the history table and to the plot. Both the table and the plot are arranged so the most recent data is at the top. Mutation Explorer also has two modes of operation. There's random, which is the default, which obviously selects a random vertex on each cycle, and round, which does a round-robin selection of the nodes in the order that they were defined in the graph. So you might ask, why would somebody endeavor to create such a contraption here? Well, it's really all the fault of this guy, Dr. Norman J. Wildberger. I've been following his work for some time now. That's absolutely essential in my research around the golden ratio. And he's recently started a new channel where he is starting this Explore Research Level Maths curriculums. And he's also started a new course, which he's calling Dynamics on Graphs. So in this first lecture, he goes through this whole explanation of what a graph is and how to play the mutation game and such, and then arrives at this, what he calls foundational exercise, which is to ask a simple question: how many of these simple graphs have a finite number of roots? And he goes on about, how important this is. And, I'm going to let him actually tell you here. Let's see.
Okay, so I do want you to spend some time on this. Time on this will be well spent. It's like doing Sudoku, but more challenging, more fun. And it turns out that the argument that's involved here ends up manifesting itself in lots of areas of mathematics. Okay, this is not an obscure argument. This argument is a kind of weaves its way into many, many different areas of mathematics. So if you understand this argument, you're already connecting, even though you may not appreciate it, with a lot of different arguments in different areas of mathematics. So I want you to really spend some time on this, and then my next video, we are going to explain this in detail, because it's really important. But it's best if you already spend many days, if necessary, perhaps some weeks, wrestling this to the ground, finding out exactly which simple graphs X have a finite number of roots.
So I've been wrestling this to the ground, and this is all new territory for me. I haven't really come across this before, but for those of you that are familiar with my work on the golden ratio, I have been building a set of tools to explore the golden ratio, and I created a video a few months ago called Exploring the Golden Ratio, where I demonstrated some of my findings around how golden sections appear within a circumscribed equilateral triangle. And, I'm just really amazed by this. And I've been trying to just put together the set of tools to try to understand this. And I know that it's going to be more than just the study of geometry. This is really a study of relationships between things. These geometric figures are graphs. They are nodes and links. They are vertexes and edges. They are, describing a field of relationships. And I think in order for me to truly understand the golden ratio, it's going to require understanding the fundamentals of relationship and how one thing is related to another, or how a whole system is related to itself. So that led to building the Mutation Explorer here, leveraging what I've learned, making the decision to build something that would be demonstrable through the browser, and use simple technologies like HTML, CSS, and JavaScript and such, and just begin to explore. I mean, he basically says, like, I'm dropping you in this field, and I just want you to go around and see what you can find. And I was really quite curious about this. So I thought the best thing to do would be to just demonstrate this. But I will mention, again, we are running in the browser here, as you can see, and you can bring this up for yourself and play around with it. Go to geometor.github.io/graphs, and we'll take you there. You can also go to the GitHub repository for this and go to the geometor.org and select graphs from there. Again, all the code is in there. You can see the only external library I'm using is something called D3 for doing the rendering of the graph itself and the data elements that you're seeing on the screen. This is a tremendous library. I have been wanting to dive into this for some time. As you know, everything is hierarchies, right? Everything is structures, and I think having, a tremendous tool set for being able to visualize this is really important. But I'm not going to talk about how all this is built today. Really, I just want to kind of take you for a little ride with me. So, as I pointed out, we have a number of graphs that we can choose from, and this X graph was the one that Dr. Wildberger used in his demonstration, and I've been building out a few others. There are some famous names here, like the A, D, and E graphs. I have a few samplings of those to play around with. I've also been creating my own, just out of curiosity. So, similar to the X graph, the triad, the quad, it was four nodes, 5 nodes in a ring. Tetrahedral relationship here, the star. A4, which is just a linear relationship. D4, which has a 3-dimensional relationship around the center. And D4b is just a little alternate on that. D4, sometimes called tilde. I'm calling it X because tilde is a problematic character in code. So, here, this is adding an extra node to an already defined graph. And then the E graphs, so E6, E6X, E7, E8, and E8b, which is just a little different arrangement. Here you see, like, the 0 in this case is out here on the end, and I decided that the 0 probably needs to be in the center. So this is just a little orientation on the number of graphs that I have selected. So let's take a look at some of these. I think, again, if we come back to X, let's run it a few times and see what happens. So we're running in random mode. We're doing 100 cycles, and as I run it, you can see it's kind of staying bounded. You might be convinced that, this is, not going to really, run out. It's going to, stay contained. But if I change it to round, you can see clearly that, we're on an exponential, grade here with the values. They become astronomical in no time. And if I reduce the number of cycles here, you can see that it's just starting to shoot off almost immediately, right? But let's go back to random and poke around a little bit. So let me see, 100. Well, what if I were to do 1,000? Would it shoot off? Sometimes it does. But we can run this and see that there's lots of different things to look at. But let's take a more interesting one, so a triad here. And you can see this very interesting pattern is starting to occur, these stripes. So there are missing values in this graph. And if we go to round, and I'll see, you can see that, this is definitely going to, take off if we do a round robin, execution of mutations. But if we do random, it kind of stays bound. So even after 1,000 iterations, we're just at negative 40 here and 12 or 15 or something like that. It's really quite interesting. But let's go back and just look at, say, 20. And we can see there's a very different pattern that's occurring here. It's not a straight line, right? So there's a gap. And what we're finding is that every third number is missing. Interesting. Three nodes in the graph, and the multiples of 3 are missing from the population sums that are here. And if we were to come down and take a look at quad, you see also every fourth is missing, and every fifth is missing. It kind of makes sense. I mean, you can think about, like, once you've come around, coming back to the first node again is going to make a jump of 2 instead of 1, and it really makes sense. But I think what's so interesting is when we go to random and say 200, we still see the gaps that are in there, but there's this kind of meandering that never gets too far from home, right? Another thing that I wanted to point out here and see if we can make it come up is that there's never a 0. The population is never 0. And any of these graphs that I've seen is through my observation here right now. It's a conjecture that from a singleton, no matter what the graph is, the population can never arrive at 0, the total population. So I don't know how to prove that yet, but we'll see. So all very interesting there. And I wanted to point out some other interesting ones here. Let's go to star here. Some of them just shoot off and the numbers become, truly astronomical. But, there are these amazing patterns that happen in the way the values progress. So you can see there's this, set of 6, or, where the gap is at 6 here, that's increasing each time. And really, really kind of fascinating. Then we have our special graphs, which are the A, D, and E graphs. And here in A4, let's make this round and go to 200 and see what happens. And you can see now that no matter how high we put this up, we are definitely bounded, right? So our values in this particular case are from -2 to 4 here as the populations are winding around, right? And here in D4, which is a simple graph, again we see the values are well bounded. But is this the complete set of root populations for this? It's kind of hard to tell. If I go to a slightly different arrangement, which was a little experiment here. So if we go back to D4 has the 0 element out here on a branch, and that's the one that gets the value of 1 to start. And I thought, well, let's just do that with 0 being in the center and starting with 1 in the center and going out from there. And it makes a difference. It makes a difference in the round robin. That's another observation here. But you can see the value is never 0, and we have a maximum of max and a min of 5 and -5. That's occurring on that. And when we go random, it really is interesting. It's kind of like a... this reminds me of the double slit experiment. I don't know if any of you are seeing that in there too. So you can see when we add another element to D4, another node to D4. We're still kind of bounded here, but we would not be bounded when we run it round robin. But we do see gaps that are occurring, which are in every sixth, I believe, here. These gaps are very intriguing to me. Then we have our E-graphs, a little different configuration. Again, you can see the meandering. Let's go 20,000 here and take a look at what it does. It'll take a little time. There we go. Yeah, you can see this. The distribution is closer in the center and dissipates as it gets out to the sides, but we have a clear bound of 11 and negative 11 that's happening on this. Adding another node. Bring this down here. Yeah. That takes us off. But look, even after 20,000 iterations, we're still staying fairly well bounded. There's something about this mutation game that's a kind of a push and pull, and it kind of limits the meandering to the context of all of the values that are in the population at the time. It can't really run off too crazily if you are running random selections on the nodes, it seems. And let's see, I'll go to my last two here. We'll go to, E7. Does the same thing, but put that down. Taking a moment there. 200. All right. So E7, E8, and E8B. And again, if we look at this round, oh, that's right. These get really interesting. So go to about 400 here. Yeah, so the E8, you can see has this repetitive pattern. It's symmetrical on either side of 0. And the same pattern is going back and forth, weaving back and forth. It changes a bit. This E8B has 0 at the center vertex. And E8 here, you can see we start with 0 here, and the patterns, it's doing a similar, back and forth, but not exactly the same. So really, really fascinating stuff. And then, of course, random stays really tightly bounded, in here. And let's see. There you go. So much to explore here. There's so much to begin to kind of, understand from, logical point of view. It's like, can we define these relationships in other ways? It's nice to observe, here and see the patterns, but can we get to the root of the pattern? Like, can we get to really understanding it? If we take a look at, let's see, about 100, how this is moving, I thought I was really kind of confused by the population, staying in one place for quite a period of time here. And I think it's got something to do with when you have a linear relationship within these graphs, and all of the values are the same, if you mutate any one in the middle, it will always come back to itself, right? So at any time that the sum of the neighbors is twice the current value, you're going to end up in the same place, right? So I think that's what's happening in here as we're walking up and down these links. We are seeing these the same values appearing for the total of the population. The population is not changing. So much to look at in all of this, and I really can't wait to get to the bottom of this. I mean, since Dr. Wildberger did the first video, let's come back to me. Let's come back to me. Yeah. So since Dr. Wildberger did the first video, he did a second, talking a little bit more about some of the attributes of a graph that would, keep it from being able to have a finite set of roots. So I'm looking forward to diving into this a bit more. Think in a future video I'm going to look at the code a bit, share that with you. Also talk a bit about D3. I think what a tremendous tool for doing this kind of work. Couldn't have done this Mutation Explorer without it. So I think that's enough for an introduction to the Mutation Explorer. And I hope you enjoyed that. And please leave a comment if you did. And look forward to seeing you in the next one. Thanks.